more manageable subproblems. With Ashi's expertise as a software engineer at Microsoft, we are poised to unravel the intricacies of recursion and deepen our understanding of this fundamental concept in computer science. Let's dive in and explore the wonders of recursion together.
Should I start? Just checking. Yeah, sure. So first, I will start with my introduction. Thanks, Ananya, for a short intro. So I'm Ashish Kumar, currently working as a software engineer at Microsoft in Bangalore campus. So in corporate, we have this culture of basically including a fun fact in your introduction. So fun fact about me will be like I am lazy for the trips, but half of the time you will find me on the trips only. So yeah, that was my intro. Let's start. I'll present my screen. Sure. Yeah. Let me know if my screen is up. Let's start. Okay. I want to make this session interactive, so I'll be asking some questions. Feel free to answer those questions. If not, I'll go ahead and answer those for you. So let's start with a recursion, and first module would be what do we mean by recursion? So what exactly is recursion? So before jumping into the recursion, can P function raise their hand? Like how many of you are familiar with function? Raise your virtual hand. It will be good enough. Yeah, okay. Some of you are familiar with the functions. So function we are basically calling as a block of code which performs a predefined task. So like for example, the weighing machine has the function of weighing to give your weight basically. So that is kind of a function. And code is basically a chunk of code that will perform a certain defined actions. So another question will be how we can call a function. So someone can unmute and tell me like how we can call a defined function. I'm hoping people on the call knows like from where we can call the functions like in the code.
By writing the function name in the main function.
Yeah, that's one of the place. Other place is thank you. Sorry, I can't see your name. So other place it would be like from the main function you can call. Apart from that, you have a user-defined function from which you are calling another function. So that is one way. Apart from that, the library functions can also call your function. So there are three ways to call a function. Apart from that, there's one other way. So every function contains a body, right? For example, this function only, it contains a body. So in the body, if we call this function again, we are calling it as a recursion. So it's basically a technique in which we defined a function, and from the function we are calling itself. So that is what meant by recursion. This is a formal definition and the understanding of the topic recursion. So let's go with the structure of a recursive function. So this is, can someone in the audience tell me what this function gonna print? If I am supplying n as one in the first call, is it not visible? Okay, yeah. Is it visible now? Anyone in the chat or on the call, people? Is it visible now? Hello. Hello.
No, it's not visible.
Let me just present my screen again. Just a white screen. Okay. Yeah. Is this thing visible now?
Yes, it's
Yes.
Okay, so this is one of the function. Can someone in the audience tell me like what this function will print? I'm supplying the n value as 0 for the first call.
it will print what is the parameter.
Yes, sorry.
It will
Yep.
print
It will print a.
It will
Okay.
print the given parameter.
Yeah. So first, when we supply this function with a value of n equals to 0, it will print out 0. Yeah. This line will take care of it. But if you see, like we are calling this function again from inside with a parameter of 1, like 0 plus 1 will be 1, and it will call this function again with a value 1. So again, it will print 1. And when we go to that function with n value of 1, it's gonna call this function again with n value of 2, right? So it's gonna print 3, 4, and till where?
infinity.
Yeah. It's gonna print till infinity. So this will create a problem, right? You don't want your code to run forever, right? So this is not the correct way to implement a recursive function. We are lacking in one thing. I'll tell you about it. Okay, I need to, I think so. Yep, window. Yep. Okay. Is my screen visible right now?
Yes.
Okay, so this we are calling is as a proper structure of a recursive function. Let's see one by one what it contains, and we have an example to go through it. So basically, you'll be defining the return type of a function as you defined in a normal function. This will be again like void, int, whatever the primitive data types are there in your language, and plus the user defined data types also. Then you will be defining the function name. So if you look at this function, this print num is basically the function name. This void is basically the return type. People on the call, are you familiar with void?
Yes, a little bit.
Okay, so basically, just a one-liner. So void is we use void when we don't want our function to return anything. So this will be the return type. Apart from that, we'll be defining the parameters as we define in any other functions. So over here in our example, this int n is the parameter supplied to this recursive function. Then we'll be calling this function again, this function name. So as I have said previously, like we call a function a recursive function when a function is executing, when we are calling the function from itself. So over here, this fn name is basically calling in the body of this fn name, we are calling this function again. So that is why this we can call it as a recursive function, but uh, it's gonna basically keep calling itself, right? So we need to give a certain base condition. We are calling this as a base condition on which this function call it's gonna get stopped. So this function name is gonna call again itself with a new parameters, and again itself with a new parameter until it hits this base condition. Then it will execute this base block and return. It's not gonna call this function again in this base block. So from there, we'll be returning all the function calls. Uh, so let's see in the example how this thing is working. So we have this function print num in which we are supplying a parameter n. What we are doing is basically printing this out, like whatever has been supplied, we are printing this, printing n. And then we are calling again this function with a new value, which is n minus 1, right? So if we call it from, so if we call it with a parameter value of 5, it's gonna print 5, right? And then it's again call, it's gonna call again with a value of 4, so it's gonna print 4, then 3, and then 2, until and unless can someone on the call tell me like when it's gonna stop?
When if condition is met.
Yeah, sorry.
When if condition is met, when n
Yeah,
is less than is greater than,
it's greater than, yeah, you are going correct.
so when n is greater than 0, it will stop.
Okay, yeah, you're half correct. So basically it will it's gonna print until we have the n value less than greater than or equal to 0, because even when the n value is equal to 0, it's this condition would be false, and we will be calling this again, and we will be printing those values. So will the output of this function will be 54321. And when at last when we call this function with a value of -1, it's this condition which we are calling it as a base condition, it's gonna get positive and we will be returning from there. Is this clear? Base condition, the recursion function calling itself, everything clear? If you have any questions, feel free to ask me in between.
Sure.
Okay, let's move to a flowchart which could explain how this function is basically getting executed. So we will have a function call to this recursive function. This can either be from a main function directly or from a user defined function. So we can have a function called as something like yeah, print something, and then it's going to call this print num. So this will be the first function call. It's going to call this a recursive function. So over here we have this print num as the recursive function. So this base condition, every time this function has been called, this base condition will be checked, like if this parameter is meeting this base condition or not. So we'll be checking this condition. Over here, the stopping condition, we are calling it as a base condition. So if it's false, it's gonna go to this recursive call with a smaller input. So over here, we are calling it from 5. We are checking the base condition. It's not meeting since 5 is greater than equal to 0. We are calling this function again with a smaller parameter. Yep, this is the flow line which represents this task. Now if the base condition is met, like when we have -1, this condition will be true. Yeah, this one is true. So we will be basically returning from here, right? Okay, doesn't work on this. So basically we'll say that the stopping condition has been met. So won't be calling this function again, and basically we'll be returning from there. How this thing works, let's see. Uh, so are you guys familiar with stack?
Um,
So basically in computer, we have two kinds of memories. One, we call it as a stack memory, and another we call it as a heap. I'll be talking about the stack memory. This is the in memory. Like this memory is basically a part of RAM only. So when we execute this, whenever we call a function in the stack, we basically put this function call. Why? It's basically memory only. So it has space in it to basically store your values or something. So let's say we have a function fn. So when we call the function, this fn block will take some space in the stack. This we are calling as a call stack because we are maintaining the call function calls in this stack. And why this basically is getting into this call stack is basically because like we generally in function we define some local variables. For example, over here we are not defining anything, but for example we need something over here, so we will be defining like a boolean or something like int over here. So that's gonna take some space, right? So it needs something in the memory. So this function is representing those memories which are gonna take by these local variables. Whatever bool or int we gonna define in this function, that space will be provided this function call. So so for the first time when we call this function prints num, it's basically it's gonna take some space in this call stack. And then what we are doing is basically printing out the value. So it's basically gonna print 5, and then we're gonna call it again with a value 4. So we will have again a function call with a value of 4, right? First we had this 5, and this is basically gonna fill with a value 4. Then we are gonna have the value 3, and so on till fn, yeah, till fn value of 1, right? Is this clear?
Yes.
Okay, no one else is responding. I'm hoping everyone is everyone is understanding whatever I'm trying to speak. Yeah, so move on.
Yes, sir, it's clear.
Okay, it's clear. So is this true, or we gonna have one more function call over here? Okay,
So can you repeat?
I was asking like, are we gonna stop at 1, or are we gonna have one more function call in this? Yeah, so basically we are calling a function with the value of 0 as well. So there will be a function call with a value 0 also. So after this, we will be returning from here. So what exactly it's gonna do in, if we talk about the memory, it's gonna pop this function. So with a value of -1, this thing gonna go out. So this we'll call it as a release of memory. We are basically freeing up the memory from here. After this, we are basically will be returning from the one function because it has already executed its block, and we'll be popping this one. Similarly, we'll be popping every function and until we have this stack as empty. Then we can call this function execution is complete. So basically we have two things in any function, any recursive function. We do certain task and we call a function. And also there's a return part as well. So we return whenever the function block has completed its execution, we return from there. So this is how recursive function actually works, and this is how memory gets allocated. I was talking about this because there's a problem with the recursion approach, and that's called stack overflow. So if you see, like, we are basically taking the space in the memory, and for any system the memory is limited, right? So these gonna take some memories again and again and again, and at last any recursive call is gonna free up the memory. So if we have many function calls, it's gonna take much memory than it's available on the system. So that condition we are calling it as a stack overflow. I think so everyone is familiar with the site as well, Stack Overflow. So this is basically a concept in which in which we are calling those functions again and again, and we are basically exhausting all the memory resources available on the system. So is this clear?
I have a question.
Yeah, sure. Go ahead.
Can you please explain the Stack Overflow thing again?
Yeah, sure. So, did you understand this function call? Like what I meant when I'm saying like fn5?
Yeah,
Sorry.
that I understood.
Okay. So basically, any function when we call, it's gonna take some space. Since we are defining any since we define any local variables in those, so it's gonna take some space. So this fn5 is gonna represent that space in the stack. Since yeah. So basically, in the first call, we are gonna call it from function 5. So it's gonna take some space with a when we call this function with a value 5. Then it's gonna call again with a value 4. So it's gonna take some space again for the execution of 4. Again for 3. Similarly, till fn minus 1, it's gonna take some spaces in memories. These stuffs. So
Okay.
all these gonna take some space until it's gonna get free. So when we call it from a minus one, it's not gonna take anything and it's gonna return. So at that time we'll be saying like the function call with a value of minus one, it's completed now. So we can pop this thing from the stack, call stack. So we pop this
Okay.
whatever space which has been taken this which has been taken by this function call has been released now. Again, we'll go back to the execution of fn0 because that call has not been completed, right? So that zero is gonna get
Okay.
completed and then it's gonna pop. Similarly, all those things all those function calls gonna get completed and all the things from the stack will get cleared out. But but when we are calling these
Okay.
stacks, there is a limited memory in the stack. So when we exhaust all those memories because calling the function again and again, then we are calling that condition as the stack overflow. Is this clear now?
Okay. So basically, Stack Overflow occurs when there are a large number of functions which are going in the stack. Am I right?
Yeah, similarly. Yeah, exactly. And this happens generally with the recursive functions because we are calling this function again and again without releasing the memories. So normal function is basically you execute the block
Okay.
and whatever spaces has been required, it will get allocated in the stack. But when the function code has been executed, like it's completed, it's going to release the memory. So it doesn't generally happen with a normal function. Is this clear now?
So it will happen with infinite one.
Not exactly with
Okay.
the infinite
Yes,
one.
please,
Like
please.
if like 2 to the power n something, if we are calling something n where n belongs to like 10 to the power 9, it's gonna get exhausted. It also depends upon the architecture of the system, how much ram you have in your how much ram you have in your system. So it's gonna depend on that. So for the if anyone does competitive programming, this is a standard. Basically, you have a limited of 1000 MB, I guess, 1024 MB. So if your recursive function is gonna take more than that, it's gonna give you memory overflow or stack overflow. It's basically memory overflow. So is this clear now? Should I move to the
Okay.
next part?
I understood.
Oh, okay,
Yes,
thank
clear,
you.
clear.
Okay,
Yes, yes.
so now will be um, guys, are you familiar with time complexity?
Yes.
Okay, so time complexity is basically defined as the operations which we do inside a function. So for a function, if we're defining the time complexity, we say like how many operations which we are doing on this function, right? So can someone in the Can anyone on the call tell me like what will be the time complexity of this function? Just think about how many operations we are doing in this function.
Five.
uh, you can say 5 for this, but we when we define a time complexity, we define it as as defined as a degree of the parameter, right? O n squared. It's basically a
Order
asymptotic notation,
and
right? Order of n. Yeah, so it's gonna take order of n. That's right. Even from the call stack, we can see it's gonna call this function again for like n number of times, and in every function call we have o of 1 operations, and we are doing this o of 1 operation n number of times, so we can say like it's the order of n. What's the space complexity? So space
Constant.
complexity, uh no, not exactly, because even if we are not defining any variable or like any array or vector on in this, even though we are basically calling using this stack, and we are calling this function again and again, so it's going to take some memory, because this function that would be in, so let me give you a better understanding. So basically in RAM, whenever we have to execute a program, we uh, transfer this code into this RAM. So if we are keeping this if we are keeping this block of code into this RAM, it's going to take some space. So, and since we are keeping this we are calling this function again and again, it's going to take some space in the RAM. And since we are calling it n number of times, this is going to take o of n space. I don't think so. It's clear. Let's move on to the other example. There I will be explaining the space complexity, and it will be more clear to you, because we don't have any local variables. I'm not able to explain this over here properly. Let's move on to the recursion types. So this thing will be quicker, because I'll be explaining faster this thing. So basically we have this 4 types of recursion: tailed, non-tailed, direct, and indirect recursion. Tailed recursion is basically when we call the recursive function at the last, basically. What do I meant by that is basically, let's take this example. 1 minute. So in this recursion call, we are basically executing, we are doing some operations, and then we are calling the function again at the end. This, so since we are doing the operations first before calling calling the function again, we call it as a tail recursion, because in the tail part we are doing this recursive call. So yep, and we have an example over here. So if we want to print values from 1 to n, and we are supplying n equals to 1 in the first call, it's gonna use this n plus 1 strategy. So we're gonna print first, and then call it again with a value of 2 and then 3. So we are doing the operation first, and then we are calling this function. That's why we are basically calling this function, not exactly this function, because it doesn't have any base condition, but if we are making the call at the last, we are calling it as a tail recursion. Is this thing clear? Anyone having doubts in this?
yes, it's
Okay.
clear.
So can someone, for this example, can someone tell me what will be the base condition? Anyone on the call? So we have to print the values from 1 to n. And in the first call, we are supplying n equals to 1. Let's say this is something not n. Let's say it's something m. So we have to print the numbers from 1 to m. And we are supplying n equals to 1 in the first call. What will be the base condition in this recursive function?
N less than m.
It's 1 to m. Yeah, so basically we need to print m also, right? So we cannot return from there. We need either we can so if I let me just type it out so that it's clear. If I type it as
N greater
n
than
less
m.
than m, sorry, yeah, n greater than m, and if we are saying like we need to return from here, yeah, then it's right. Sorry, I got confused. Yeah, so basically n greater than m will be the base condition for this function. We'll be returning from there. Let's move on to the non-tailed recursion. So when we call the function after doing the operations, we are calling it as a tailed recursion. So it's obviously going to be opposite. So if we are calling the function first, then we are executing the operations. We call it as a non-tailed recursion or head recursion, right? Simple only. Okay,
Yes, sir.
so now let's talk about the direct and indirect recursion. So direct recursion we call when we call the function from itself. It's basically these all are examples of the direct recursion. Since we are since we are making the recursive call from the function body itself, this is called direct recursion. And if we talk about the indirect recursion, let's say this print num. This print num is not calling print num, it's calling print num1. And in the body of print num1, yep, sorry, we are calling this print num. This is basically a body. So directly we are not making the recursive call to this print num. What we are doing is basically calling another function in this print num body, which is gonna in turn call this function. So it's basically the indirect recursion. And and this indirect recursion we don't use it. I haven't in like till now I haven't seen any use case where I have used this indirect recursion. Are these things clear?
Yes.
Okay. So now let's move on to the binary search. So how many of you guys are familiar with the binary search code? Acha, how many of you want me to basically tell you about the algorithm of binary search before jumping into the recursive function for binary search? People on the call raise their hand or something that I can see like how many of you want me to explain binary search. Okay, I think everyone is familiar. So I'll just explain the algorithm once so that it's clear before jumping into the recursive version of the binary search. So this binary search is basically an algorithm to find a key in an array. So if we have an array of 15, 22, 34, 36, 51, 63, 75, we are having this array and we want to check if we have a value of 75 in the array or not. So what will be the basic approach for this one? Anyone on the call? How can we search a key in a linear array?
Using binary search.
Yeah, sure, binary search, but are there any other ways to check it out?
Linear
Yeah.
search.
So, if we talk about the basic search algorithm, there will be linear search in which we'll be going to every element and we'll check its value. If it's equal to the value which we are searching for, then we'll be returning like, yeah, this value is present. Otherwise, we'll be saying, yeah. If we reach the end of the list, we can say like none of the values match the value which we are looking for. So we'll be declaring it as the key is not present in this array. The other approach will be the binary search. So if I talk in brief about the binary search, it would be like we will directly go to the middle of this array and we'll check if first thing is basically it's only being applied to the sorted array. So if this is a prerequisite for the binary search, if our array is not sorted, we cannot implement the binary search. So over here, our array is sorted. So we can implement binary search over here. So in the mid, we'll directly go to the middle element. And if it's equal to, if this thing is equal to the key, then we can say like the key has been found and we can declare it like the key is present in the array. If it's not, we can check like the value of the key. If it's basically less than, if it's basically less than the middle element, this element, sorry, if it's less than this middle element, we can say like for sure the if the value is present, it would be on the right side of this array. And if value is basically greater than this middle element, we can say right this whatever key which we are searching for is definitely gonna be present on the right side of the array if it's present in the array, right? So this is basically the sorted thing. That is why we are able to implement this binary search. It's because the array is sorted. So one thing, can we implement the binary search if the array values are equal? For example, there are duplicate elements in the array. Can we implement the binary search? Let's say we have another 22 over here, another 63 over here. Now can we implement the binary search? Can we use basically the binary search to find the key? Anyone on the call? Yeah, so definitely we can use this thing because like even if we go to the like one of this 22, we can say like if this 22 is whatever the value which whatever the key is basically if it's less than 22, we can basically say like if it's less than 22, we can say like it's gonna be present in this part. So either way, this binary search can be implemented if the duplicate elements are present. So after this, we'll be basically saying that our left whatever was our search space, it has been reduced to this part. We'll be searching in this part. Again, we'll be fetching the middle and check its value. If it's less or greater, depending upon the case, we'll be going to either left side or the right side. So over here, we were searching for the value of 75. And since it's greater than 63, we'll reduce our search space to this. And now we are having just one element. So if it's equal to the key value, we can declare that, yeah, the value is present. Otherwise, we can say it's not. Is this thing clear? Binary search?
Yeah, it's clear.
Okay, so can we write a recursive function for doing this binary search?
Sorry?
Can we write a recursive function to do this binary search?
Yes.
Okay. Can you tell what your approach is gonna be?
First, we find the middle first, and then we recall the function.
Sorry, your voice is breaking.
We find the mid,
Okay.
and we check if it's greater or smaller than the search.
Yeah.
and then we eliminate the part which is completed, and then we will recall.
Okay. Yeah, let's do it. If you're saying like it can be done, let's do it. So let's say it's a bool bin search. So what will be the parameters of this?
Start and end.
Okay, start,
Search.
end. Do we need anything else in this recursive function? We gonna need the array, right? If we are not declaring it as a global, we need that array so that we can check whatever value is there. So what you want to do in this?
We're gonna
Yeah.
we're gonna take the array as a
Your voice is very less. Hello.
hello.
Yeah. Yeah. Go ahead.
Yeah, we'll take array as one parameter.
Yeah. 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 All these things have been done. What you want to write in the body?
For the recursive version,
Yeah. Yeah. For the recursive approach of this binary search.
we'll write the function name.
Okay. You want to say bin search again, right? Function name.
Yes,
What do you want to supply as a parameter?
the new start and end.
Okay. How we are going to define this new start and end?
We'll have to check if the
We'll
search
have
is
to.
less
Okay.
than or greater than the mid.
Okay. So basically, we'll be fetching out the mid index, right? First.
Yes,
It will be end minus start divided by 2, right?
yeah.
Okay. After that will be what will we do?
Now we will check if it is
We'll
less than
check.
or greater than the search.
Okay. Okay. What we have to check for? Key, right?
Yeah, for key.
Okay. So we'll be checking if our mid value is basically less than key or not, right?
Yeah.
Okay. So if it's less than key, then
Then we will take end as mid minus one.
yep. So basically, when the mid value is less than key, right? So we're gonna take end as,
Mid minus one.
but let's see this case. If for example the mid value is 36, right?
Okay.
And we are checking for the key 75.
Yeah.
So this condition will be true, right? 75 will be greater than 35, right?
Yes.
So can we say like we need to check on the right side of the array, right side of the middle?
Yes. Yes.
So what will be the new start and end in that case? It's
Start
gonna
will
search.
be mid
Start
plus
will
one.
be mid plus one. Yeah, that's correct. Mid plus
And
one, and
end
end
will
will be
be
same, right?
same. Yes.
Okay, and the key, whatever is there. And if it's not the case, then
Then end equals to mid.
okay, we will say like start's gonna same, but end is gonna be mid. That's true. And key, yeah. Okay, what will be the base condition? Can someone else tell me apart from my friend? Anyone? What will be the base condition in this? So we have defined our recursive calls, and I'm hoping this is correct. So When we can say like we have found the element or we haven't found the element.
Search and key equals to mid.
Okay, let's see first, like when this is gonna hit like base condition, like what could be the last possible case where we can call these things. So every time we are basically reducing our search space, right? So basically we are reducing the number of elements on which we have to search. So if at first we have n elements in an array and we are reducing it, so at last we can only have one element, right? Should we check if the array is empty? Should we check for key if the array is empty?
Sir, can you reshare your screen? I think it's stuck.
Okay, okay, yeah, sure. Is this visible now?
Yes.
Okay. So I was saying like basically we have at start n number of elements. We are reducing its search space. So at last we could have only one element. So does it make sense to check for the key if the if our search space has become zero?
No.
No, right? So our base condition will be hit when we have only one element, and if that element is basically equal to key or not. So if this last element is basically equal to key, we can say like this key is present in the array. And if it's not, we can directly say like this key is not being present in the array, right?
Yeah.
Okay, so basically what we'll do, it's to check if the start is less than or equal to, no, the start is equal to end. If the start is equal to end, we can say there is only one element, and that particular element has been is being represented by the index of start or end, since both are equal in this case, right? Yeah, so this condition will be hit when we have only one element in our search space, and the index for that element will be start or end. In this case we can check like if a of start is equals to key or not. If it's equal, we can say like C out key found. And if it's not, we can directly say C out key not key not found. Key not found. Does this base condition make sense?
Yes.
Everyone on the call, right? Anyone having doubts on this whole function? Okay. What will be the time complexity of this function? Let's see. Let's see. What will be the time complexity? Reshare my screen. I don't think so. It's gonna be visible now. Stop sharing. Yep. Yep. So this is our recursive function for binary search. Let's talk about the time complexity of this one. So we are basically calculating of the calculating mid. This is a constant operation, so we can call it as O of one thing, right? Apart from that, all these comparisons are basically one operations only, constant operation. So it's gonna take O of one. So in the block, we don't have any for iteration or anything to basically increase the time complexity. So whatever will be the time complexity of this recursive function will depend upon the number of calls which we are making, right? Uh, Let me explain this again. So in this recursive function, we are basically doing only the constant operations. We can count like how many operations which we are doing. First, we are checking if the base condition. This is one. This is one operation. Then we are calculating the mid. This is second operation. Then we are checking if it's less than key or greater than key. This is third operation. So basically we are doing three operations. This is constant number of operations. So we can say like in the function we are basically doing constant number of operations. So it's O of one. So how many times we are calling this function will determine what is the time complexity of this function. O of one, sorry, into calls. Let's see how many times we are gonna call this function. So at first, let's see in terms of array size because we are reducing out the search space. So it's basically it will be more clearer in terms of array search space. So first our search range was basically n elements, right? Then we move to n by 2. Then our space is gonna get reduced by 2. So it's gonna n by 4. Or I can write as at n to by 2 to the power 2. So if we have more elements, like if it's not the end, like if 75 was not the end, then we will be having, for example, all these elements. And for that, we'll be having n divided by 2 to the power 3 and so on. So in the last level, we're gonna have n divided by 2 to the power k. Let's say if we have k levels, k calls. So over here, you see this is one function call. This represents a first call in which we are checking the value of 36. Then again, we called it and this represents the second function call in which we are checking the mid value of 63. And then we are checking again for the mid value of 75. So every time we are calling, right, we are reducing the search space by 2, whatever was there. And at last, if we say like when we reach the level k, we are having only just one element, right? So this will be equal to 1. So after k levels, if we are having only one element, then we can say n divided by 2 to the power k. That is our current search space is equal to only one element. If we solve for k, we'll be seeing like it's equal to log base 2n, right? It's simple math. Basically, we'll be shifting it to
Yes.
this side 2 to the power k, and then we are solving for k. 2 is gonna go in the base logarithm. So this will be log 2, log n base 2. So and every level is basically representing one call, right? So we'll be having k calls, and the k value is basically log n. So our time complexity will be O of 1 into log n base 2. So we can call it as log n. Is this clear? Or this was too complex or anything? It was too simple. Uh, should I repeat this thing? हाँ ना कुछ तो बोलो. Okay, I'm gonna repeat this again. Is this code clearer to you guys? A recursive version of the binary search? People on the call, is this thing clear? Okay, I'm assuming this thing is clear and I'll be explaining the time complexity again. Assuming this code is clear because it's a simple thing. We are checking if
Yes, sir.
the...
Yeah.
Okay, it's clear, everything, right?
Yeah.
Okay. Can people on the call write a recursive function to find the value of x to the power y? We need a recursive function. Let's call it as a power. And this power should, if we supply it with a value of x and y, this recursive function should return the value x to the power y. Can we write a recursive function for this? First, tell me if it's even possible.
Yes, it's possible.
Okay. So if it's possible, can someone tell me the approach?
I think every time we decrease by one
Okay. Yeah.
and multiply x by
Multiply
x by itself.
this thing. Screen is visible, right?
Yeah.
Okay. So you are saying like we can have x to call this function again. Let's say pow. Or power. Power is actually a function, library built-in function. We are basically calling this function with a value of y minus 1, right?
Yes.
This is what you meant.
Yes.
Okay. What will be the base condition in this?
Y greater than zero.
Y.
Greater than zero.
Okay. If we no, base condition is basically the condition on which we're gonna terminate those recursive calls. So if y is greater than 0, we want this thing to get executed, right?
Yes.
Because like if we call it with a value of 5, it's this thing needs to get executed. So base condition should be false for these things. So what will be the base condition on which we are saying like we have the constant value and we don't need to call this function again?
When
Y not equal to 0?
So 5 is basically not equal to 0, right? And even in that case, we want this power to be called with a value of 4. So that's not true, not
y
equal to 0.
equals to zero.
Yeah, so if y is equal to 0 and anything with the power of 0, we have that value as 1, right? So we don't need to call this function with the y is equal to 0. So our base condition will be y equal to 0. Y will be equal to 0. We can say, right, this value is 1 and return from there. And while returning, let's say for any call, this power was basically x comma 0. We call it with x comma 0. This gonna return 1, right? And then it's gonna get multiplied with x. So, and this will be the call with a value of 1, right? X comma 1. X comma 1 is gonna call this x into power of x comma 0, and this is gonna return 1, this thing, and it's gonna get multiplied with x. So for this x comma 1, we are having we are having the return value of x, right? Simple. So, and this will get called by power of 2, and where it was called, it's gonna get multiplied with x. So this is gonna return x to the power 2. Yeah, so basically this thing is correct, this approach is correct, only one thing is missing. And let me just write it so that it's more visible. Yep. So we are saying int of power x comma int of y, and we are saying if x no y equal to 0, we are saying return 1, otherwise we are returning x into power of x comma y minus 1, right? This is correct, right? Anyone think like this is not right? Okay, there's one more thing. It's basically y can be negative also, right? This thing can be supplied with y as negative,
Yes.
right? So in that case, if y is negative, this thing's gonna execute forever, right? Because if y supplied as -1 is gonna call -2, -3, -4, minus till infinity. So we need to write one more condition. It's gonna be a edge case. If y is less than 0, we don't want to return any valid input. So either we can return -infinity or something, or any value which can indicate like y is negative and this function is not defined to handle this negative value of y, right? This is one thing. Apart from that, what will be the time complexity of this? Okay, this is basically the after session task. Like you need to find the time complexity of this power function.
Okay.
Let's move on to the next thing. I'll present my screen again. Screen. Yep. That was all about the recursive function. No one has any doubts on the recursive version, right?
No. Sir.
Okay, let's move on to the last thing, backtracking. So let's understand it with a problem. So we have a problem where need to print the subsets of a array. Everyone knows about subsets, right?
Yes.
Okay. So what will be the subsets of this 1 to 3 array?
1, 2, 3, 1, 2, 2, 3, 1, 3. 1, 2,
Okay, yeah. So basically we have what we call as subsets. We want to print all the subsets of this given array. So this is the problem. So we need to find solution for this. And we'll be having a recursive approach since this topic is recursion. So I cannot tell you any other approach. Otherwise, there exist other approaches, actually better approaches. So we'll be talking about the recursive approach to tackle this problem. So what will be the approach? Let's see. So what we'll do is basically for any subsets, we have two values, right? Either include this, if we talk about a particular element, right? Let's say 1. So for any subsets, either we include this one or we do not include this one. And that is how we'll be forming any subsets, right? Either we will include this one in the subsets. So we'll be having the subsets of 1, 2, this will be one subset. Then we can have a subset 1. So the only element which will be present is 1. Or we can have 1, 2, 1, 3, and kind of that. And if we don't include this, we'll be having the subset of 2 comma 3, or basically 3. It's only 2 only. So if we include 1, we will have some subsets, and if we don't include 1, we'll be having another subset. So for every element, if we decide if it's gonna be present in the final set, we'll be ending up having a subset. Otherwise, we'll be having another set of the subsets. Similarly, we can do this thing for 2 as well, 3 as well, right? Is this thing clear? Yeah, everything gonna be relying on this.
Yeah.
Okay. So for every element, we'll be exploring 2 possibility. Either we will be including that or we'll be excluding that. So let's see for the 1. So for 1, we'll be going to this basically check, and first we'll be including the 1, right? So if we are checking the possibility of including the 1, we'll be ending up with these many possibilities, right? Where we'll be having a subset with 1 or 1 3, 1 and 3, or 1 2, 1 2 3. So the right subtree will represent all the subsets having 1 in the subset. And if we are not including 1, we'll be ending up with the left subtree, in which we won't be having this 1 as an element in any of those subsets. So over here we are having a null subset, then we are having a subset with a 3, then 2, then 2 3. So all these situation corresponds to the case where we are not including this one. Then if we go to the right subtree again, now we have included 1. Now we have a choice to include 2 or not. So if we include 2, right, we will be saying, right, we'll be ending up with the possibility of these subsets. And if we don't include 2, we'll be ending up with the possibility of these subsets. So you are seeing like a decision on any element to either include it or exclude it. We are basically landing up on a set of subsets. So basically we are landing on a part of solutions. So this thing will continue. We'll be checking for 3, and if we are including this, we are ending up with a subset of 1 2 3, and if we are excluding it, we are ending with a subset of 1 and 2, right? Is this approach clear?
Yeah.
This thing is clear, right? So basically this is the approach we can use to fetch all the subsets of an array. One more thing in this would be let it be, talk about it later. So can we have a function for this, like code for this approach? So no one asked me like what is basically this backtracking. I explained you the whole approach, but no one asked me like why we are calling this recursive approach as backtrack. What we are doing different over here is that we are calling this recursive solution only as the backtrack solution. Okay, so this backtrack, we are calling this recursive approach as backtracking because what we are doing is basically we are exploring out the possibilities. So we have explored the possibilities, like this possibility corresponds to including 1 2 and 3, all these 3, right? When we land up on this solution, we don't want to end it over here. We are basically going back, and we are basically undoing what we have done. So over here we have included 3, and when we are going back, we are basically saying like we have included 3, right? But now we want to undo the step and we want to take decision on this 3 again. So we are basically backtracking our way. We are basically landing upon the solution, and we are going back again to explore other possibilities. So the other possibility over here is to exclude the three. So this step is called backtrack, because going we are going we are going back to our previous state, and we are exploring other opportunities. So since we are doing this solution is called backtracking. Is this thing clear?
Yes, sir.
Okay. Let's move on to the code part. Also, there's this formal definition of the backtracking. So if we are searching for a solution for a particular problem, over here we have this problem, and among all available options, so all are these available options. And if you are trying to find a solution set, so in this I'm just talking about the analogy with the definition so that you can understand well. So this is the solution set, and we are developing the solution one by one. So this is basically the first step, this level. This is second step. So we are doing this step by step, and we are increasing the levels. Obviously, these are the levels, and we are using the recursive calling. So we'll be seeing like why we are using recursive call. So by definition, this approach can be called as a backtracking approach for this problem, print all subsets. So can someone tell me what will be the approach for writing the code for this solution? Anyone? We can analyze, right, what we are doing. We are basically getting an array, then we are making decision on the element. Like if my current context is basically this element, let's say if it's not on this element, if my current context is making decision on this second element, then we are basically either including it or excluding it. So when we are including it, we need to make the call to this function again, so that it can make decision on this three again, right, on the next, basically on the next element. But here we don't have any element. So basically what we are doing is basically it's having a context on which we need to make a decision. So over here we are making decision on two. So we have a context for making the decision on two, then we are making decision on three, and then we are either including it. So we are making again this call to make the decision on three, to include it or exclude it. So basically this is why we are using the recursive call. Let's see the code for this. Already present. Yep. Screen is visible, right?
Yes, sir.
Okay. So what we want to do is to print out all the subsets, right? So we can have the function as print subsets. What will be the parameters to this function? What are the things we want? Yeah, so it's simple. We want this array, right? We want this array. We want this. If I am using vector, we want this vector to be present. And then we want the index, like the context I was talking about, the context on which we want to check, like the element on which we want to check. So the first thing will be the vector. Guys on the call familiar with vector, right? Using vector over here.
Yes.
Okay, so we are using vector. Then we want the context on which we want to check. And we want like how many elements have been included or excluded. So we want something like when we are making this call from to decide on two, we want this call to know like one has already been included, either include two or not include, right? So we want the current subset elements. So for that I can have another vector. Sorry. which will represent the current subset. Let's talk about the return type of this function later. So what we want to do in this is basically decide on this, right? The current index. So we have two opportunities, either to include it or exclude it. Writing the same thing. What we'll do first, include it. So for including it, we need to have this current subset to hold this element, right? And if we are including it, for example, we are over here, we included one in the current subset, then we need to make a call for deciding on two, right? The next element. So we'll be making the call for deciding on the next element. Same with idx value. What will be the idx value in this case? The context. Anyone? So we need to decide on the next element, right? So we need to check on the idx plus one value. Yep. So what we are doing now is basically, if we are supplied with this vector 1, 2, 3, we are basically exploring these opportunities. So we are basically including one and we are making this call. Then we are again including two and making this call. Then we are including three and making this call, which is gonna land and print the subset, right? Now we want to go back. Yeah, go back from here. Land it on this state. And this will be done while returning of the function, right? This, when this call has been completed, it will go back to this state. And in this state, we have included three first to make this call. So we want to remove three and then again make this call, right? Is this clear? This is the backtracking step.
Yeah.
Okay, so basically we are undoing what we have done. So we have basically included this a of idx value to the current subset. Now we want to remove it. So pop back is the function, I think so. Yeah, so we will be popping this thing from the current subset. And again, we want to decide on this other, another, like the next index, right? Next element, what we are going to do with that. So basically we will be calling this function again. With idx plus one only, and the current subset will not include this a of idx value. So we are basically exploring both these opportunities, either to include the current element as well as to exclude this current element. Is this right? Sounds right, right? uh, is this thing not clear, or like if it's not clear, I can explain this thing again.
Yeah, it's clear.
Okay. Yeah, it's clear. So basically, these are the operations which we needs to do to get the current subset. When we want to say like the execution for this block has been completed, we cannot include the element now or exclude the element. When we can say that, just look at the update parameter, the parameter which has been updated in every function call. These two, right? So when can we say like the function calls has been done and we want to say like we got the subsets? Like for example, over these situations, we can say like we got the subsets and we don't want to call the functions again. We are doing this when we have no other elements to explore, right? So this is happening when the idx value, the thing on which we need to decide, is basically greater than the last element, and the last element will be of the vector will be n minus 1, right? When the idx value is greater than n minus 1, we don't want to call any recursive function, and we want to say like, whatever is being there in the subset, we want to print that, right? So that's would be the base condition for this. So if the idx value is greater than or equal to, you can say no, right? So if the idx value is basically greater than the last element or equal to, it's equal to, greater than won't be the condition. If it's equal to the size of the subset, we can say like we don't have any value corresponding to a of n. So over here, whatever is being there in the current subset, it represents one of the solution. So we'll be printing that. Right. So this is gonna print the subsets. When we reach the base condition or the condition on which we don't want to execute things further, on which we don't want to decide, then we can say like we have the current subsets, right? Since we are not returning anything, I think so the return type would be the void. Is this function clear for the subsets?
Yeah.
I think so. Time has already been completed. So can we check time complexity for this function once? Yep. Let's check the time complexity from the figure. Yep. So from the figure, we can check out the time complexity even. So what we are doing over here is basically making the function calls. At every step, we are making two function calls, right? So this will be one call. This will correspond to two call. This will be the 4 call. This will be the 8 call. So this is 2 to the power 1. This we can write as 2 to the power 2. This we can write as 2 to the power 3. So if we are making k calls in this, right? K calls. If we have k levels on this will be the last thing will be 2 to the power k, right? So how many calls which we are making? 1 plus 2 plus 4. These many calls will be making, and in every call we are doing constant operation, right? This pushback, pop back, these are the constant operation because we are popping and pushing from the back. If you're familiar with the vector, you will know like this is a constant operation to insert at the back and popping from the back. So every call is doing O of one operation, and we are making these many calls. Let me write it over here. One call, then two call, then 2 to the power 2 call till 2 to the power k call. Oh, what will be the summation of this geometric series? I think so. It's basically a into r. R will be 2 to the power n. Since we are making, since we are having k elements over here, we can say no. It's basically n. So minus 1 divided by 2 minus 1. So the formula, if you know, is basically a to the power r, a into r to the power n minus 1 divided by r minus 1, where r is basically the geometric difference that is dividing the successive term with the previous term. 2 to the power 4 divided by 2 will be 2. So our value is basically 2. So it's 2 to the power n, right? If we denote it as the asymptotic notation, we can say this -1 should be neglected and we'll be lefting with 2 to the power n. And in each call, we are doing O of 1 operation. So the total time complexity will be O to the power O in O of 2 to the power n. Yep. Is this clear? Time complexity? Basically mathematical thing else, I think. Okay, yeah, so that was it about the recursion as well as backtracking. Does anyone have any doubt in any of the things which I have explained?
I don't know.
No, right. So I think so we can conclude this topic. I'll be sharing the notes with your club members. They can in turn share with you guys. And if you have any doubts, please reach out to me on LinkedIn. I'll be happy to answer your doubts. And thanks for this opportunity to Code Campus. Yeah, that's all. Closing this out.
Thank you. Yeah,
Yeah.
and you can continue.
Ladies and gentlemen, what an insightful session we have had today. A heartfelt thank you to our esteemed guest, Ashish Kumar, for sharing his expertise and shedding light on the fascinating world of recursion. Your insights have broadened our understanding and inspired us to tackle complex problems with confidence. To our dedicated Code Campus community, thank you for your active participation and engagement. Your enthusiasm fuels our learning journey and makes DSA Unleashed a thriving community of learners. Let's also extend our gratitude to the organizing team, sponsors, and partners for their unwavering support in making DSA Unleashed a resounding success. Until next time, keep coding, keep conquering.
Thank you, Ashish.
Thank you. I'll be leaving. Thanks for this opportunity. Yeah.
Thank you. Thank you. We are
Yeah.
grateful.